We left off on Monday discussing testing proportions. And we said that the base calculation was to assume that we had a normal distribution for our population underneath where we were calculating our proportion. And again, our idea is the same. To calculate a Z calculation score, by taking the calculated proportion P and comparing it to the benchmark proportion P pi 0, dividing by the standard error for the proportion, which is based on our benchmark. And then again, our same idea for everything else follows from here. I'm going to have a Z critical based on our sensitivity alpha, our significance level. And if it's too far out, then we reject our null hypothesis. So I said we were going to do an example today. Page 300 and write down what page number it is. 346. Problem number 49. Down here at the very bottom. A hospital shipment of 3,500 insulin syringes. 14 of them are defective. Well, I got 3,500 syringes, and 14 of them are defective. At a 0.5 sensitivity, alpha equals 0.05, is this sufficient evidence to reject future shipments if the hospital quality control requires 99.7%? Thank you, Brian. 99.7% usable syringes. We had 14 unusable syringes. There are actually, now that I've written this down, there are actually two different ways to think about this. What I've written here is based on the number of good syringes. But what I've written here is X. That was the number of bad syringes. So I think this is the wrong proportion. If I need 99.7% to be good, what's my maximum threshold for bad? So if I have a rejection rate of bigger than that, then I need to reject this supply. Okay, there's a statement right there. What's my null hypothesis? What's my alternate hypothesis? What am I trying to test? Insulin syringes are very, very thin, usually 30 or 32 gauge needles. If you get an insulin needle that's not usable, whether it's dull, bent, or isn't drilled cleanly all the way through, that's a life jeopardizing issue. Insulin delivery in cases of glycemic shock looks like somebody having a heart attack. They go down, they're flushed, they're atrociously palpitating. It's a disaster. You need to be able to react very quickly. What am I testing here? But I need to know, should this supplier continue to sell me syringes? So I need to know, is their rate of error lower than? If it's lower, then I'm going to keep them. If it's bigger, then I'm going to trash them, right? So my assumption is the null hypothesis is that everything's okay. And the alternate hypothesis will be, there's a problem here. If the null hypothesis is everything is okay, then the null hypothesis should be that my proportion is less than or equal to 0.003. That would be the good thing. I could keep them. And my alternate hypothesis will be that it's too big. You could do it the other way around. You could use 0.997 and count good syringes instead of bad syringes. But if the number of bad syringes is too big, I shouldn't use these people anymore. Okay, too big. I want a right tail test. I need to know if it's too big. I don't care about too small. I only care about too big. Okay, I need two pieces of information. I need a calculated Z, and I need a critical Z. The critical Z value strictly comes from the table. What's the critical Z value? You should already have this number written down from the stuff we did last chapter when we did confidence intervals. I'm looking for the 5% line down there. My area is 0.05 in each tail. And we're looking at one tail. What's the 5% for one tail?
0.645.
If I go to the table itself, I look for the area to be 95%, right? So that there's 5% in the little tail up here. Okay, 1.6, well, there's 0.45 is between these two, so 1.645. So that's my critical z-value. And I want the positive one because we're doing a right tail. What's my calculated z-value? I have some other calculations to do before I can actually figure that out. Because this calculated z-value requires something I haven't calculated yet. What's P?
I think it's
Right, we take the number of bad syringes out of our group. So we had 14 over 3,500. Minus the benchmark 0.003 over square root of 0.003 times 1 minus 0.003 over 3,500. Because that's how many pieces we had. Out come the calculators, bunch of math happens. Tell me what you get.
possible.
14 divided by 3,500 is 0.004. So when I do the top here, I get 0.001. Then to do the bottom, it's 0.003 divided by, I'm sorry, multiplied by 1 minus 0.003 divided by 3,500. Then I take the square root of that. And I take that goes on the bottom here, so 0.001 divided by that number. I'll call it 1.082. 1.08 would actually be good enough because my z table only goes up to 2 decimal places. So this is our calculated answer. Now make the decision. Do we keep this supplier or do we pitch him? We can decide here. We could do another calculation if you'd rather to get to our decision. But now that I have this number, I can actually make a decision here. How would I make the decision based on this number?
You keep it because it's not more than the critical value.
We only reject when we're outside. Since we're looking at a right tail, I would need this number to be bigger. It's not. So I cannot reject my null hypothesis. My calculated value is inside the boundary established by my critical value. It's not bigger, it's smaller. How would I know whether or not this was a normal population and this was a valid test? We had a rule, especially when dealing with proportions, on how to decide on this from last chapter.
Like the opposite.
Okay, what do we have to do with those numbers? So 0.003,
But then more than 10.
aha. What are these numbers? Well, I'm pretty sure that 99% of 3,500 is pretty damn big. Probably bigger than 10. What's this number up here? Which is bigger than 10, even if it's just barely. And that means that this one is 3489.5, which is also way bigger than 10. So yes, I can assume this is a normally distributed population. So I was good using a z-test. If I had come up with a no here, I should have used a t, not a z, or I should have gotten a bigger sample. Not 3,500 needles, maybe I needed 5,000 needles. Those are my two options when I don't have a normal population. What's the other way I could have made my decision? How do I find the p-value? What p-value? P is based off of the calculated value. I would like to know the chance that Z is bigger than whatever we calculated. And we calculated 1.08. So you can either look that up on your table or use the calculator or use Excel. You can give me what this value is. What is this value? 1.08 gives me this number right here. 3599. But that's the area in here, and we want the area in the tail. How do I get the tail? Subtract that number from what? Not in this case, because I'm using this table. Because you'll notice that we only shaded in on the right half. It's a half. So it's 0.5 minus 0.3599. Which is 0.1401. What does this p-value tell me? I'm hoping it tells me the same thing that we got up here for our decision. But I only reject when p is small, right? So I got to go back and I got to look at alpha. And according to my notes and to the statement of this problem, our alpha was 0.05. This number is bigger than 0.05. I don't reject. Exactly correct. I'm very happy to see that because it means these two results tell me the same thing. I'd like to get confirmation more than one way that I made the right decision. Now, we're talking about insulin syringes. What are my two possible errors? What's a type 1 error here? A false positive. Okay, what are the consequences of saying this is a bad batch of needles, we need to go to somebody else? It's expensive. I have to throw out all these insulin needles that I just got or return them, and then I have to go buy from a different supplier, which I may get a different cost on, and I may have a problem. I could run out of needles as I'm waiting for this new shipment to come in. How many people need insulin needles at this particular location? What's a type 2 error here?
It doesn't work, but you say it does.
Which means we keep them, but there are too many errors. And that means that we may end up using a bad needle at some point and not catching it. Or we may have more bad needles that we send out in the public, and all of a sudden, people using insulin at home have a problem, and we need more hospital trips. So which is the worst balance? Our goal usually is to reduce type 1 errors. When we reduce type 1 errors, we have the possibility of type 2 errors. Remember, there's a trade-off between those two. We have to be careful, though. Questions? We did a one-tail test here. Because I said, it's okay if we have fewer bad needles. It's not okay when we have more bad needles. When we do a two-tail test, we split the area for our rejection zone into two pieces. Here's our right tail test. Here's our two-tail test. But that means that the Z threshold gets higher. So you are less likely to reject the null hypothesis in a two-tail test than you are in a one-tail test. Because this number will be higher up than this number. 99% of the time, two-tailed test is going to give us higher thresholds and thus will be less likely our rejection area gets smaller to reject. That means fewer type 1s, but potentially more type 2s. Questions? Problem number 51. To encourage efficiency, Catalog Call Center issues a guideline that at least half of all phone orders should be finished in 2 minutes. The most annoying thing I ever had happen to me working one of my first jobs at a drive-through was they put a clock on the drive-through. I know every restaurant does it. There's a clock on that. How long did it take for this order to get filled? Same idea. How long does it take for this person to order on the phone? I know 99% of catalog orders now are done online. How long does it take to go through? We could do the same idea. A random sample of 64 phone calls shows 24 calls lasted less than 2 minutes. Are they meeting their goal? Or did we just get a bad sample? So I want to test the proportion of calls finished in less than 2 minutes. What's my null hypothesis? Things are okay if state the appropriate hypotheses, assuming that we are counting the proportion of all calls completed within 2 minutes.
Like the proportion is greater than or equal to 0.5.
50%, right? At least half of all my calls. Okay, so I can start with that statement. The null hypothesis, things are okay if my proportion is bigger than 50%. My alternate hypothesis then? Okay, so now I can start right there. Now we had 64 calls and we had 24 of them that were finished in under 2 minutes. Based on this, are we doing a one tail or a two tail? What was that, Max? One tail, because it's two tail is only equal or not equal. This is just looking at less. And if it's just looking at less, are we doing a right tail or a left tail? Right tail or left tail? I'm looking at less though. Left tail. Now, why do I need to know that? Because the Z value I'm going to be looking for is negative. It's on the left. Okay. Let's calculate. The textbook actually asks me, find the p-value So I'm not even looking up a critical value yet. I just want to find the p-value and make the decision that way. That's what the part in the textbook says. Find the p-value. All right, so I need to start with my calculated z. I got to fill in all the right numbers. It's something minus something. What's the left number on the top?
24/64.
My calculated proportion. Okay. 0.375 minus. What goes here? 0.5, my benchmark. Over square root of 0.5, 1 minus 0.5 over the number of things. One minus 0.5 is also 0.5. What do you get when all is said and done? Yay. Hey, I have a really good advantage here. I can go directly to table C2 and look for the z-value -2 to get the proportion, to get p. What is the chance z is less than -2? That's in table C2, the cumulative distribution version. Because I went all the way from the left to -2. That's this picture. There's -2.0. 0.0228. Hate my pen. So that's my p-value. I can't make my decision yet because I'm still missing a piece of information. Piece of information am I missing? What's not up there?
I don't think we wrote down alpha.
I haven't been told alpha yet. As a matter of fact, that's something that we can decide on now. Do we want to be 95% confident, 90% confident? What's our one tail alpha? Now, the textbook actually tells me alpha is 0.05. What do you decide? I need you to fill in the blank. Reject or do not reject. What do I do to compare? What did you tell me about up here? Here, the p-value we reject when p is small. We didn't reject there. Here is the p smaller than the alpha we want. Here's our p-value right here. So in this case, we do reject. The picture in my head, every time the picture says, hey, I'm doing a left tail. We're way down here. P is way down here below our cutoff. Now, we didn't actually get a critical value, but that's the other way to do this. If I have alpha equals 0.05, then the critical Z is negative 1.645. And then I could say, oh, I'm going to compare those two. -2 is smaller. It's outside, so we could reject that way as well. Now, the bigger question, is this statistically significant or just practically significant? Suppose I said that the other way around. Is this meaningful? Is this important? Or is this just an anomaly of the statistics? Well, when we did this test, we said we want at least half of the calls to be 2 minutes or less. But in our class, in our group, what percentage of the calls were less than 2 minutes? 37.5. That's substantially less than 50%. That's substantially a real issue to whoever's managing this call center. Somebody's going to say, no, we got to get faster here, people. You're taking too long, whatever it is. So this is actually practically significant, not just statistically significant. Questions? If we have a non-normal population for a proportion, I shouldn't use Z. Crap, what can I use instead? I could, since I'm looking at does it or doesn't it, and there are only two options, could use a binomial. Could do this with the binomial distribution, assuming it was discrete instead of continuous. That's acceptable. Page 346, example 9.3. Well, they call it case study. Mini case 9.3 goes through one of these. More often we use normal as an approximate for binomial. But if we have a non-normal distribution or a significantly large or small n value, sorry, x value, like we had 14 bad needles, we only needed 10 bad needles to say it was normal. But if I'd only had 7 bad needles or 5 bad needles, I wouldn't be able to say, oh no, this is a normal population. If I only had 5 bad needles, I could say, well, what's the chance that we had 5 or fewer? That's a binomial distribution. 5 needles or 4 needles or 3 needles or 2 needles or 1 needle or 0 needles. And I can do that in Excel fairly directly. Questions? Yesterday, during my office hours, I sat down with the manual for my graphing calculator, and I learned something new, thanks to mine. Under that same stat button, where we were doing our lists to find means and medians and descriptive statistics, and we were asking it to calculate things, there was our one variable statistics. Well, it turns out that next column says tests. We were doing a z-test for a mean. We were doing a t-test for a mean, right? So I said, hey, let's calculate a z-test. And it gives me a way to put in either the summary statistics. You know, I've got stats blinking there at the top. I could put in my benchmark, my standard deviation, my sample, and then I could ask it for a two-tail, a left tail, or a right tail. and it'll calculate for me. And when it does that, it'll give me a p-value. Wait a minute. That p-value is 0.175. If I'm doing a one-tail test, 5%, I'm not rejecting. Even at 10%, I'm not rejecting. Take the null hypothesis. Do not reject it. There's my answer. I can also, in that same test section, actually give it the data. If I tell it I want you to use the data, then it says, where is the data? The data would be in one of my lists. So I go back to stat, edit. There's a data pile of lists right there. And I say, oh, this was the example we did about filling the bottles on Friday. Well, okay, in that case, my average was supposed to be 10. And my standard deviation, I got to go back and look at this problem. Standard deviation for this. Oh, no, I don't have to worry about the standard deviation. I had to worry about the population standard deviation. What did they say? They said in this problem, they expected this to be 0.05. I got to go find it. 0.07. And then it'll calculate. Now we were doing a two-tail test for that one. There's my p-value. At alpha being 0.05. Don't reject the null hypothesis. These bottles are filled fine. The only thing I noticed here is it won't let me do proportions. It won't do the standard error with pi. It'll only do it with means. T-tests, same process. Stat, test, there's a t-test. If I have a small number, because I only had 12 in that list, I should have done a t-test, not a z-test. There we go. P-value is 0.448. Don't reject the null hypothesis. It also does give me the calculated t-value and the calculated z-value in both of these cases, so I can do it either way if I know 1.645, 1.96, or 2.23. Those were the three t-values, z-value criticals we were using for 90%, 95%, and 99%. So it is possible to do all of this without resorting to Excel or without resorting to a t-table, a z-table, if you've got the fancy calculators. I decided that this was a really good idea. And so on our Canvas page, I posted the chapter from the manual for the graphing calculator on how to do statistical tests. It's right here under reference files, the second object, statistical tests. Please feel free to use that whenever you want. But if you do that, tell me that's how you've done it and copy down the numbers it gave you so that I know what you got and I can match it with what I get. Questions? Then I will see you all on Friday. We have last Friday. And we'll start the next chapter. And that means the homework in chapter 9 is due on Monday. We'll see you all on Friday.